Hey friends, what's up? Today we're gonna solve this particular problem that's available on LeetCode. Says find the peak element. Okay. Let's read the problem once. It states that a peak element is an element that is greater than its neighbors, right? So if you are given an input array nums and where nums of I is not equal to nums of I plus one, so you can assume we are going with this assumption that two neighboring elements won't be same. Okay, so yeah, you have to find the peak element and returns its index. Cool. Yeah, so an array can contain multiple peaks. In your case you can return any one of the peaks and that's fine. Okay, the first solution that comes to my mind when I'm trying to solve this problem is pretty easy. Like if you look at the first test case is 1 2 3 1, right? Pretty simple, man. I mean, just do a linear search, and for every element, checks whether that particular element is greater than its neighbor or not. But the problem is the time complexity for that is going to be O of n. Can we do better? Yeah, obviously. That's why they're asking this question, dude. So yeah, let's see. I mean, let's try to figure out how we're gonna alter our binary search and gonna solve this question, right? So, okay, whenever you're trying to alter binary search, always remember the whole point of altering the binary search is in a way that you have to reduce your search space, right? So whenever you have found your element, you have to check how you're gonna move. Okay, so what I mean by that is how you're gonna go either in the left half or in the right half. Okay, so let's do that. So if you can take the first example, 1 2 3 1, right? So I mean, how I generally approach like the binary search problem statements is I always try to first write the condition on which the mid element would be met, right? So I've just written that. So if a of mid is greater than a of mid plus 1 and a of mid is also greater than minus 1, so peak element, so a peak element is one which is greater than both of its neighbors. So if it is that, then I return mid and I'm done with it. Okay, if that's not the case, right, then oh, we should know either it exists in the left half or in the right half, right? So if you take this example 1 2 3 1, right, and you can see 1 2 1 2 3 1, right? So the answer in this should be 3, right? Because 3 is a peak element, it's greater than 2 as well as it's greater than 1, right? So that's what you want to return. So the index you want to return is 2. Okay, can you observe one thing over here in this particular example, right? If you see that 1 2 3 1, so it's an increasing suborder, right? So if so what how I have read, like how I have tried to search these left, like the right space here is that if it is an increasing subsequence, that it is in this case, so 1 2 3, so it's increasing, right? So there's no way that peak element is gonna exist in the left half, right? So we're gonna search in the right half, right? So yeah, so this is how I'm doing it. So it exists in the right half, else continue in the left half, right? So let's check whether that logic works on this particular case or not. Okay, so always don't try to come up with a solution straight away. Try to come up with a solution that tries to match our use cases, right, or our test cases. So that's gonna help you to debug it better and you're gonna come up with the solution. So this particular way of solving is called TDD, where you always try to write a certain set of code that helps us to meet those particular test cases, right? So let's go on to the next example. 1 2 1 3 5 6 4, right? So it's written over here. So the mid element over here is 3. I'm gonna simply apply my previous logic. That was if it's an increasing subsequence. I mean, it's not increasing subsequence because 1 2 1 you can say okay 2 is a peak element, but I am assuming that if its previous neighbor is less than that, then it's an increasing subsequence, right? So I check for the mid element, right? So this is also in the increasing subsequence. So I continue to search in the right sub half, right? Once I go on to the right sub half, so this this now becomes my search space, right? So this is 4. If you see, so low right now is 3. So it's 0 1 2 3 4 5 6, right? So 6 plus 3 is 9. 9 by 2 if you do is 4. So now our mid actually points to 5. And if we apply the condition, right, or this condition at 5, so that returns our answer, right? So index 5 could be our peak element and we're good to go, man. Oh no, I'm sorry, I did something wrong. What is wrong with me, man? I'm so sorry. So 3, if I go here, so our mid mid becomes 6. Okay, how our mid becomes 6 is like 0 1 2 3 4 5 6, right? So 9 by 2 is 4.5, right? So that's 5. Yes, so our mid right now, okay, for this search our mid is gonna be 4. Sorry, I mean it's gonna point at index 4, but the element that is being stored is 5, right? So again the same logic, right? So it's a 3 5, so it's an increasing subsequence. So we continue to search in the right subhalf again, right? Search in right half. Okay, so if you see here, now our element mid is 6 and our condition for finding the maximum element is met, so we return 6, right? So it is working. Okay, so now this is the code which I have written. It's doing exactly what I just told you, right? So we have initialized low, we have initialized high, and we have initialized mid, right? So mid is low plus high by 2. So you'd be asking, okay, why have you written this and this condition when we were not discussing it, right? So these are basically to handle the terminal cases where mid is either pointing to the first index or at the last index, okay? Because it is, so we have this assumption, right, where your very first element and the very last elements is negative infinity, okay? So it's always advised to read your question, right? So we check, okay, if this condition is being met, then return the index, else our previous condition, right, if it is an increasing subsequence, then check in the right subhalf, else check in the left subhalf and return low. So you can return anything here, low and half, because according to our condition, if you, so this loop will only quit when low equal to high, right? So yeah, so if we submit it and ta-da, done. So yeah, that's how you actually solve this. I hope you like the video.